Hello there, and welcome to this week's recording in which we will be deriving the Einstein field equations, and we will be doing that from the Einstein-Hilbert action. So yeah, we may as well begin. This may end up being a longer video, I'm not entirely sure. Certainly a big bit of tensor-y stuff. Hopefully it will be quite enjoyable. Anyway, let's begin. So the first thing we can do is define the Einstein-Hilbert action. So we know that the total action S is the sum of the gravitational action and the matter action. So that's S sub G, that's not a G, S sub G plus S sub M. Now we can find this, that's fine, but what we need to find is the gravitational action, also known as the Einstein-Hilbert action. So S sub G here we take as the integral of the square root of minus G times R, where R is the Ricci scalar, which is the simplest coordinate invariant scalar non-structurable from the metric. The metric signature here being minus plus plus plus, minus plus plus plus, and hence we end up with this Ricci scalar. Ricci, and no idea. And d to the 4x. And what is G here? G is the determinant of the metric tensor. G sub mu nu. So I can write that. Mu nu. That's the wrong way around. And we'll choose units. Units. So that 16 pi times the gravitational constant is equal to 1. And we'll deal with constants at the end. Anyway, to find the equations of motion, the Einstein field equations, what we want to do here is, of course, vary the action and set that to 0, which is, of course, the principle of least action, which I've covered various times across this channel's history. So we'll go straight ahead by saying that the variance of S here, delta S, is of course going to be delta times the integral. I'm going to move the d4x to the front, times the root of minus G, G being defined above, times R plus the Lagrangian of the mass, and that entire thing equals 0, which we know from our initial equation. And we're just gonna look into, because we can find that. That was a really nice L. I'm not used to doing them like that. Anyway, we're just gonna expand the gravitational part here to say that delta SG is equal to the integral. Is equal to delta times the integral d4x of delta minus root minus G R, and that can be expanded as the following. That's why I got confused, that's not supposed to be there. d4x of, delta minus G R plus root minus G delta R. Cool. With R being our Ricci scalar even. So what we need to do here, what I'd like to do is evaluate this separately and this separately, or in fact evaluate that separately and that separately, because that's doable. So we'll begin with the variation of the determinant. first of all, we'll come up with some variation of just g, and then we can plug in root minus g. So delta g is, of course, delta of our definition of d, which is the determinant of g nu. Just pulling the formula out of, if you've ever done a tensor course, linear algebra course kind of thing, you'll know that this would be the determinant, and then we're only taking the delta on the g base mu nu. So we've got our exponents at the top here, nu, delta g mu nu. But of course, we're varying with respect to the inverse metric g to the mu nu here. So we can use the identity, using identity, g to the mu alpha, g sub alpha nu is equal to delta sub nu. I always thought of this as like a weird version of the chain rule from basic calculus. I don't know why that always made sense to me. I've never even tried to derive it, so I have no idea if it comes from that, but logically. Anyway, we can vary our identity here. That's identity. Vary identity g mu alpha g sub alpha nu is equal to 0. And we can split that apart and say g mu alpha times g alpha nu plus g mu alpha times delta g alpha nu is equal to 0. We know what we can multiply everything by g mu beta. Again, beta is just another indice. So g sub mu beta delta g to the mu alpha g alpha nu plus g mu beta g to the mu alpha d alpha nu. That's not an alpha, that's an a. Equals 0. Now we can see from our identity above, by swapping these two indices, we get beta mu g mu alpha, which is our identity from up there. Again, can be applied, and hence that's just delta sub beta to the alpha. So we can say that g mu beta g alpha nu delta g to the mu alpha plus delta g beta nu is equal to 0. And swapping stuff to the other side, delta g beta mu is equal to minus g mu beta g alpha nu delta g to the mu alpha. Yeah. And now we can put this all back into Jacobi's formula. Jacobi's formula. I'll learn all the names pronunciation one day. Anyway, from there we can say that delta g is equal to g to the beta nu delta sub beta nu. Yeah, from our above stuff. And of course we have a expression for that is equal to g to the beta nu minus G mu beta G alpha nu delta G to the mu alpha. Once again, upon expansion, which I will probably do, beta nu, I'm going to write it this way, mu beta delta G to the mu alpha. We can see that part again, using our identity above, simplifies down to just delta base alpha to the beta. So we get that this is minus G delta alpha beta. That's not a beta. G mu beta delta G mu alpha. Which simplifies because we get rid of some things. Did I forget something? No. No, that's alright. Yeah, which is just minus G mu alpha delta G mu alpha. Yeah. No, I'm happy with that. So that's our delta G. Of course, we're trying to vary root of minus G. So first of all, let's write that in terms of delta G. So delta root minus G is equal to, we can say 1 over 2 root minus G delta of minus G. That makes sense. Yep. 1 over 2 root minus G minus delta. We can bring that in, which is 1 over 2 root minus G times G mu delta G mu nu. Wonderful. And since, yeah, G over root G, so G over root G is just minus the negative, so it's just minus a half. So that's the minus from there, and then it's root minus G, which comes in here. Root minus G, G mu nu, delta G to the mu nu. Cool. That's a familiar sight. Anyway, the next thing we have to do is vary the Ricci scalar. Now we can actually formally define that as G to the mu nu times R sub mu nu. So our variation here, delta R is equal to delta G to the mu nu R sub mu nu. Keep writing in English instead of Greek. So delta, I think I'm just tired. G to the mu nu R sub mu nu plus G to the mu nu delta. Stop saying mu nu every time. It's getting really tiring. Mu nu. First time is already in the form we need. So that's fine because it's proportional to. Okay, that's alright. But the second term we can do stuff with. Palatini identity. Which will derive from the Christoffel symbols. So we derived the Christoffel symbols, I think, in one of the past videos. I don't remember which one. You should just watch them all and then you'd know. Coming from the person who made them, that is. I also can't remember. R mu nu is equal to the Pth partial That is rho. It should be rho. Trying to remember. Yep. The Roth partial of Christoffel rho sub mu nu minus the Newth partial of Christoffel rho sub mu nu, mu rho even. The combinations here always get me. Rho mu nu sigma, rho sigma minus Christoffel sigma mu rho. Hope we don't run out of space here. Christoffel rho nu sigma. Nu sigma. Right. Some of these aren't tensors. So, yeah, this isn't a tensor. But delta of that varying that is a tensor. And so we can take the covariant derivative of both sides. Of the delta mu nu. So the alpha, this is just for some general Christoffel symbol. Is going to be partial rho alpha mu nu rho lambda sorry, I need to lock in for cycling of constants, which is always a pain. I'm not gonna have space. It's fine, I'll fit in. There we go. Lambda, and that should be rho nu. This one should be mu lambda. Yeah. That's the covariant derivative variation. And now we can use locally inertial coordinates. So locally inertial coordinates where that's equal to 0 at some points, but delta gamma is not equal to 0. Yeah. Varying the Riemann tensor here would just simplify. I'm not going to write it all out again. Nu sigma mu nu rho is equal to this. Yeah. And we can just contract indices here to get Ricci tensor variation, because obviously we don't have 4 indices. R mu nu is equal to delta rho delta gamma rho mu nu minus, contracting indices, by the way, by letting rho equal to sigma. Delta mu rho. Cool. Yeah, that looks like the Palatini identity. I'm gonna double check my notes. That is the Palatini identity. Okay. That's used to have. So getting that, we're just gonna go back and integrate now, because we're getting bored of all this extra work. So if we take our integral from earlier, which is the unholy looking thing. Or actually, we can just sub it into the second part of this, which is this part. This part? No. It's the part of the integral. Yeah, it would be expanded. I'll write it out for simplicity's sake. Minus g mu nu delta r mu nu is equal to. Now this is our integral. I need to do this right. That should be that from above. That goes in there. I don't have space. Right, we can do a connection here. If we know that g mu nu is compatible, I don't know if that's the right symbol for compatibility, but that'll do. With the connection, this sub lambda del sub lambda g to the mu nu is equal to 0. Yeah. Then we can move it inside the covariant derivative. So g mu nu, wrong way around, delta. So it's just what I said basically. Cool. And that should not make any difference. We could also say the same thing for nu, which I'll write out. Cool. And we can relabel indices to extract a total divergence here by letting rho equal g to the mu nu delta gamma to rho by mu nu minus g to the rho mu. My eyes are hurting. Delta lambda mu lambda. Yeah. And so we get a total divergence of that. Cool. That's an integral that I don't feel intimidated by. I'm happy with that. Let's do some things with it. Stokes theorem is one. Generalized Stokes theorem on a manifold. Over some m d4x root minus g. It's not a row. Is equal to this over that. Again, you can see exactly, even if you haven't done algebraic topology or whatever this comes from. And sub row d, that's just our surface. And obviously, I mean, this is basic like inverse square law, but we can assume that the variations of the fields at the bound the brain is just barely braining today. I'm not sure how I've made it this far, and I'm still happy with what I'm writing, but it's alright. What I was trying to say is we can assume that the variations vanish at the boundary of infinity, because at that point r squared would of course be very small. Thus, the boundary integral here is 0, and hence our original integral is also 0. So that's nice. Oh dear. Yeah, that is nice, I promise. But now we need to combine everything and vary it. So this is... I'm going to write in a smaller text, and I'm probably going to shut up and concentrate for a second so I don't get this wrong. Cool. Yeah. And writing that all that was kind of pointless because we know with that half of it drops out anyway. It would be this term drops out. And now we can factor out that. No, that we can factor out. So that's equal to 4x root minus g of r mu nu minus half. Right, we're getting somewhere. The last thing we need to do is the matter action, which isn't so bad. So Sm is our integral over our Lagrange. That wasn't as nice as... But my other one was so nice, and now I can't do it. That's alright. But okay, that'll do. Lagrangian of m root minus g d4x. This is just the energy momentum tensor. No, it's not. It involves the energy momentum tensor. What am I saying? Which is T mu nu 2 over root minus G delta of the matter action. That's what I was thinking about it. So rearranging stuff around, this is true. That's all to counteract if you bring that around to the other side. It's the... Yeah. It's the yeah, he says. The factor of -2 in this and -1/2 there is convention to match physical the definition of energy density. So that's where that comes from, if there is curiosity. My textbook noted on that, so I thought I should also make it known. Anyway, nearly done. Of course, we demand the total S to be equal to 0, and thus SG, capital G, plus delta Sm is also equal to 0. So you subtract the two integral terms, and you get that the integral d4 x root minus g r mu nu minus half r g mu nu g nu minus half t mu nu delta g tele mu nu is equal to 0. This is arbitrary. And hence the term in the parentheses vanishes identically. And of course, if the integral is equal to 0, then the product inside is also equal to 0. And so we say that r mu nu is minus half r g mu nu minus half t mu nu is equal to 0. More commonly seen. And of course, based on our units from earlier, we get that r mu nu minus half r g mu nu is equal to 8 pi g t mu nu. Einstein derived the Einstein tensor g mu nu is equal to r mu nu minus half g mu nu, which gives us the very nice equation g mu nu is equal to 8 pi g t mu nu, where t is the energy momentum tensor. That's lovely, but it's usually written in a different form, which is taken by tracers, which I really hate, but it's okay. They're not that bad. It allows us to write the equation of the Ricci tensor directly. So instead we say that g mu nu r mu nu is minus half g to the mu nu g sub mu nu is equal to 8 pi g. I'm just gonna get rid of it for the sake of traces. GT. Pi GT for r is equal to minus 8 pi. And we can sub r back into our original equation. So r mu nu plus 4 pi g mu nu is equal to 8 pi nu, and we rearrange to get r mu nu and pull out the 8 pi. I'm going to pull out 8 pi. R mu nu is equal to 8 pi g t mu nu minus a half t g mu nu. Boxed. Yay! That was certainly a 1. No, it's certainly a thing. This is probably the most challenging thing I've done on here so far. So I hope you enjoyed. If you did stay till the end, I would be wholly surprised, to be honest. 35 minutes of me rambling and scribbling on a blackboard. Not even a real blackboard. But at the very least, I hope it was vaguely interesting. I certainly found this fun. I go with eye-opening activity. But yeah, I hope you very much enjoyed, and I will see you again next week. Goodbye.